Hello and welcome to another extra exercises video. We're in week 5 now and we're looking at a whole range of important topics this week, including vectorization, manipulating arrays, and starting to work with functions and debugging. You'll see in this bunch of exercises that there's quite a few that essentially ask what's the output of this chunk of code, and while it might seem like it's easiest to just go to MATLAB, put it in there and find out, what I actually want you to do is work through on paper or on your computer and just think about it line by line, like what will this line output? And the reason that I'm suggesting you do it like this is because this sort of thing is a really good candidate exam question. So this is the sort of thing that you could be asked to do on paper, which makes it good practice for you to be doing it now. The other thing you'll notice is, like the last couple of weeks, this is a video made up of videos from multiple recording sessions. Again, that just happened as part of our semester to trimester transition when I rearranged some content. The chapters in the description will line up with your task sheet, so just follow those as a guide and everything should be okay. Enjoy the rest of the video. So let's have a look at our warm-up exercises first. So we've got two loops. On the left, we've got a for loop for I equals 2 to 3 to 15, display I. So we've got our start point is 2, we're going to be going up in steps of 3, and we're going to stop once we pass 15. So we'll start with 2, add 3 to 5, add 3 to 8, add 3 to 11, add 3 to 14, and that will be where it ends. And we can, of course, check that in MATLAB. So we'll go for I don't think I'm sharing my MATLAB screen. Let's actually share that. For I equals 2 to 3 to 15, display I, and if we run that one, we'll see that we get that 2, 5, 8, 11, 14. So definitely use MATLAB to check, but try and think about the logic of how it's going to run before you jump over to MATLAB and type it in. So on the right-hand side, we have our while loop question. So we start with I equals 1, and while I is less than 20, we're going to add I and display I. So this one's going to be a little bit trickier. We're going to want to do that one step by step. So what I might do is I'll actually type it in, and then we'll just sort of write what's going to happen line by line in the comments. So I equals 1, while I is less than 20, I equals I plus I, or 2 times I would be another way to write it. And then we're going to display I. So on our first pass, I will be equal to 1 plus 1, which equals 2. So 2 will be displayed. I might actually put in pass 1. And in pass 2, I is equal to 2 plus 2, which equals 4. So 4 will be displayed. In pass 3, I is equal to 4 plus 4, which is going to equal 8. Then on pass 4, I is equal to 8 plus 8, which gives us 16. Now, by the time it sort of checks the condition, it's still less than 20, so we will do a 5th pass. So pass 5 is I equals 16 plus 16, which will give us 32. At that point, I is greater than 20, so we'll break out of the loop and move on with any code that's left. In this case, there is no code left. So what we're going to see displayed is 2, 4, 8, 16, 32. It just doubles every time. So we'll run this code and confirm that we're right, and there you have it, 2, 4, 8, 16, and 32. So those are our little warm-ups on loops. Okay, so exercise 3 is writing vectorized code. So vectorized code is just about avoiding for loops and trying to just apply math directly to the vector. So let's firstly have a think about what this code's doing. We're creating some vector, and then for every element in that vector, so for every index, we're subtracting 3 from the element at that index. So we're taking the first element of A and we're subtracting 3 from it. We're taking the second element of A and we're subtracting 3 from it, and so forth. So when we display that at the end, everything will be 3 lower than it is. So we can create that code just to, again, see how it runs so that it's clear. So we'll see that, and it might actually be easier if I actually display the original A as well. So I'll display A up here so that we can see the difference. So every element in the new A is 3 lower than it was before. The easier way to write this is as follows. So the vectorized form, we would have A equals 2, 1, 3, 4, and we would simply go A equals A minus 3. And then again, we can display A so that we can see the difference. We'll display both A's. So you can see that we've got the exact same output that we had from the for loop, and all we had to do was type this one line of code. That one line of code subtracted 3 from every element. So that's vectorization. You can also do it with multiplication and division. So that's vectorization in a nutshell. We also have vectorized relational operators. So again, we'll talk a little bit about the outputs of each of these, and then we'll actually see how it works. So we've got this big long array of a bunch of different numbers, and then a few different relational operators applied to it. So when we apply a relational operator to a vector, so here we've said display A greater than 18, that's pretty much going to return ones where it's true and zeros where it's false. So we'll do it for the first one, and then we'll talk about the rest as well. So A equals 19, 16, 17, 20, 28, 15, 17, and 31. So disk A greater than 18. So what we're going to expect to see is 1, 0, 0, 1, 1, 0, 0, 1. So everywhere that A meets that condition, it'll return 1. Everywhere it doesn't meet that condition, it'll return 0. So let's run it, and then you can see it. It's not lined up very well. Probably would have been nicer if that was aligned, but you can see that 19 resulted in 1, 16, 0, 17, 0, 20 is 1, 28 is 1, 15 is 0, 17 is 0, and 31 is 1. So it's an array of logical responses. And the way that might come in handy is you might want to calculate how many of the numbers were over 18. If you're doing, say these are ages, you might be doing some sort of census statistics. So the same sort of logic applies to the rest of them. So for A less than or equal to 25, we're going to get ones where that condition's met. And I might actually just replace this line so we can see it a little bit more clearly. So we're going to get ones where it's met, zeros where it's not. So we're going to get 1, 1, 1, 1, 0, 1, 1, 0. So mostly ones with 2 zeros in the middle. And you can see that has happened there. So 19 is 1, 16 is 1, 17 is 1, 20 is 1, 28 is 0 because it is greater than 25, 15 is 1, 17 is 1, and 31 is 0. So you're probably starting to get the gist of where this is going now. So if we then do A is equal to 16, it's going to return pretty much all zeros except for where it's actually equal to 16. So we'll have 0, 1, and then 0, 0, 0, so on and so forth. And you can see that there. So the only one that had a 1 is the one that met that condition. And lastly, A is not equal to 17. So that one's going to be true for everything except 17. So it's going to be 1, 1, 0, 1, 1, 1, 0, 1. Because it's true when something is not 17 and it's false when something is 17. So we'll run that. And you can see that that's what's happened. So 19 is 1, 16 is 1, 17 results in 0, and again it results in 0 over here. So the only zeros are where it was equal to 17. So it works pretty much the same way as a relational operator for individual, a scalar value, but it applies it to each element in the array. Alrighty, so let's have a look at the any keyword. So this is another, I guess it's a relational operator of itself. It just kind of summarizes the results of relational operations. So the any keyword works on if any of these conditions are true. So it basically says if any of the ages are less than 18, so if any of these return true to that relational operator, then display don't let into the bar. Otherwise, enter the bar. So it's looking for any ones in here. And if any ones exist, then it prints this message. So this one's going to output don't let into the bar because we do have a few people that are less than 18. But just so that you can see it for yourself, I'll actually leave that array there because it's the same one. So if any A less than 18, display don't let into the bar. Else display enter the bar. And if we run that one, we'll see that don't let into the bar message. If we replaced our A array with, I don't know, let's go a 19-year-old, 20-year-old, 30-year-old, 89-year-old, then we'll get the other message of enter the bar. And really this should be, oh no, that is right. I thought it was the other way around, never mind. So yeah, that's only going to return true if none of these are ones. And we can actually also check what that looks like so that you can confirm it to yourself. So you can see that there's some ones there, which means that they're not going to be let into the bar. That's the any keyword, and it's a good way to kind of have a quick check whether any of the conditions are met or not met. So the other option is all. So the all keyword checks if all of them are ones. So what we would want, so here we want to rewrite the code here in exercise 5 to use the all keyword instead of the any keyword while achieving the same program functionality. So we're trying to achieve the same bartender logic of we're not going to let anyone in the group in if anyone's underage. So we can restructure this code as an all statement. So pretty much we want to flip it all around. So I might actually just leave that one there so you can see the difference. Actually no, because you can see it on the screen, so I'll get rid of this. So if all A is greater than or equal to 18, we want to say enter the bar. So if all of them are ones, every single person is greater than or equal to 18, we let them into the bar. Otherwise, don't let into the bar. And for our current group, we should see that it doesn't let them into the bar because we do have those younger people in the group. And there you have it, don't let into the bar. So that one's looking for all of them to be ones. So A greater than or equal to 18. As you can see, there's plenty of zeros in there. So if we did get rid of those younger people, let's leave them out on the curb, then it's going to be all ones, and then it's going to say enter the bar. So that's how the any and all keywords work. Hopefully that makes sense. They can be pretty handy for kind of large logical processing. Okay, so concatenating these two arrays. So the output of the following code, well, actually there's not going to be any output because it's all suppressed, but let's imagine that we've then displayed C and D. So for C, we've used a comma, which means that these three are going to get added straight to the end of these three. So it'll become one row vector with 1, 2, 3, 4, 5, 6. D has used a semicolon. So the semicolon here means start the next row. So we're going to end up with a 2D matrix in this case with 1, 2, 3 on the first row, 4, 5, 6 on the second row. So again, it's going to be easier if we visualize that, but it is important to think about it before you go typing it straight into MATLAB because you'll be required to do some stuff by hand for the midterms. So C equals AB and D equals A colon B, semicolon I should say. And you can see that C, as I said, was a row vector of those 6 numbers, whereas D has been transformed into a 2D matrix with the 1, 2, 3 at the top and 4, 5, 6 on the next row. So that's concatenation, that's combining two vectors or arrays. You can also do it with multiple matrices and stuff like that. So yeah, if you need to. I can't think of too many cases where you would need to in this subject, but you can. And then indexing matrices to pull numbers out of it. So matrices are a little bit different to just vectors. We touched on a little bit in week 4 and also this week in week 5. So let's type these in and then we'll sort of talk about what's going to happen. So this array here is going to look something like 16, 18, 19 on the first row. So that's before the semicolon. The semicolon says go to the next row, so the next row is then going to look like 17, 20, 21. So that's what our A looks like. So the question asks, question A asks, write 3 different lines of code that use indexing to return the value of 21. So there's multiple ways to get to 21. 21 is the last element here. It's also in the second row in the third column. So we can do the row column format of A row 2, column 3, so row first, then column. So that says go to the second row, go to the third column, and there you have it. We can also do just sort of the linear format, I guess you could call it. So this one is actually going to go through and count them this way. So this would be 1, 2, 3, 4, 5, 6. So A6 is going to return that element because it's the 6th if you treat it as just a single array, like a one-dimensional array rather than a 2D matrix. And lastly, because 21 is the final element, we can actually retrieve it using the special end keyword. So the end keyword takes the last element. So we can run this and confirm that we have in fact gotten the right indexing for all of them, and you can see 21, 21, 21. So we have successfully found 3 different ways to extract 21. So again, it kind of is up to you a little bit, but the easiest format, in my opinion, is the row column format because you're giving very specific addresses. You also, it can get a bit confusing with this linear format because you might be tempted to go across and then down, so across the row and then down, but that's not actually how it works. So if I was to index A3, it's actually going to return 18 because it goes 1 is 16, 2 is 17, 3 is 18. Whereas in my brain, at least, I would have imagined that it would go rows first, then columns. Sorry, across a row, then down to the next row, so across the columns. But instead what it does is it goes down, and then across, and then down, and then across. So I prefer the 2D format, the row column format, but completely up to you what makes sense to you. And the end keyword is very, very useful if you want something at the end. You can also index something that's like a step back from the end. So you can go n-1 and it'll return 19. You can also go end to end and it will return the end row, end column. So you could kind of mix and match a little bit. You could say I want the end of the first row and it will give you that. So there's actually sort of those 4 ways, I guess, to get 21. So that's part B. It also asks us to use range indexing to return 16, 17. So I'll just kind of condense these a little bit. So range indexing is where we take an entire row or column or part of a row or column. So in this case, it wants the entire first column. So return 16, 17. So what we would want to do is we would want to use the special colon symbol, which says take the whole, oh, sorry, actually we want to go, yeah, actually, sorry, I was right. So that's saying we want to take all of the rows in column 1. So the colon is all. So all rows in the first column. And that will give us the 16, 17 because that's all rows in column 1. So let's run that and confirm, and then you can see that's worked out for us. So we also want to write code that uses range indexing to return 20 and 21. So 20 and 21 are the second and third elements of the second row. So what we can do is we can say return 20 and 21. So we want the second to third element of the second row. Oh, sorry. We want row 2, the second to third column. You can see I still mix up my rows and columns a little bit, but that's saying go to row 2. So row 2 is this one, take the second to third element. And if we run that, we'll see that we get the 20 and 21 that we wanted. Alrighty. Next up, we have logical addressing. So this question asks us to write code that uses logical addressing to create an array named B that contains values greater than 18 from the matrix shown in exercise 8. So that's the matrix we just created. So logical addressing is where we use indexing to create a new array containing only the values that meet a particular condition. So in other words, we want to extract all of the values from here that were greater than 18. Yeah, greater than, not greater than or equal to. So the way that we can do that is we can go B equals A, brackets, A greater than 18. So that says I want all values of A where A is greater than 18. So this is going to return with our ones and zeros like we saw before, and then this is going to use that to determine which elements to keep. So if we run this, you'll see that we get the 20, 19, and 21, which were the only ones that met that condition. And there's no zeros or anything else where the other ones were false. So you put the array you're extracting from and the condition you want to use to extract from it. And that was it for our logical addressing question. So now we're going to have a look at writing functions. So question 4 asks us to define a function that has these characteristics. An output x that includes the result, represents the result. The function name will be sum2. The reason I'm using sum2 is because sum is already a function in MATLAB, so we don't want to overwrite that. And we'll have an input argument a that represents an array. The word array implies that it'll be one-dimensional rather than matrix, which would imply it's two-dimensional. So we can assume that our input is one-dimensional. So the output should be a sum of all the values in the array, which we're going to achieve using a for loop. So the other thing we need to pay attention to is when we save our file, we should give it the same name as the function. And then we're going to test it with a few different arrays. So let's open up our new file. So when we define a function, we start with the keyword function, and we put in the output, which was x as specified in the Word document. And then we put the equal sign, the function name, which is sum2, and then the input or inputs if there's multiple. There can also be multiple outputs. Now, something that's not compulsory, but that I tend to do is I also include an end. The reason I do that is I find it's a little bit easier to see where one function starts and the other ends when you've got multiple, which you will do later in the semester. So MATLAB doesn't actually require it anymore, but I do find it helpful. So yeah, that's kind of an optional thing. And then the way we can actually implement this function, I mean, you might have a slightly different way, but here's how I would do it. I would set x to 0 to begin with. And then I would go for each element I in A, add that element to x. And that's it, because that x will update as that code runs. And then when it finishes, it contains the value that it should. It contains the overall total. So if I run this now and save it as sum2, obviously it's going to throw an error because I haven't given it an input, but at least it's been saved. So I could do, say, 1 to 4. So that's going to be 1 plus 2 plus 3 plus 4. So that's 3, 6, 10. I could also do, let's say, like 1, 3, 5. And that gives us 9, which you can see is correct if you add those numbers up yourself. We could also do like 0.1, 0.2. We'll get 0.3. I'm using sum rather than sum2. Whoops, let's actually test our own function. We should get the same answer as sum. So sum2, 0.1, 0.2. And you can see we're getting the same values as the actual sum function in MATLAB. So that's a pretty promising start. Cool. So that appears to be working the way we want it to. That's great. And the last part of the week 7 exercises is to actually add some documentation to the functions. So documentation is really important for explaining how your code works and making it easy for someone to understand. So all inbuilt MATLAB functions have documentation. We've touched on this in class, but if you ever get stuck, you just sort of say help. And let's use a common function that we've used a bit, plot. So when I type that, the documentation starts like this. It has the function's name, followed by like a very, very short description of what it is. So, you know, that doesn't really add much extra information at that point. Then the next line actually tells you
what it does and what the inputs should be, what the outputs should be. So if, well, actually this one doesn't show you outputs because it doesn't really have any, it just generates a plot, but other functions do have outputs in there as well. So if we wanted to write our documentation for sum2, the way that we would do it is we would go to the line underneath the function definition, put out the cent sign for a comment, and then we type sum2 and, you know, give it some brief description, sum of elements. Then on the next line, we could add that extra detail. So x equals sum a calculates the sum of all elements in the one-dimensional array A and returns as the value x. Something like that. So now if I run this code again, it's going to throw an error. That's just sort of how I save it. So if I then go help sum2, you'll actually see that information that we've just entered. So exactly as we typed it here, it's now appearing there for someone to read and understand how the function works. So that's it for week 7, actually. I'll just actually mention for documentation as well, it's really important that you do this for your assignments and stuff, because it makes it easier for us to mark. And the easier it is for us to mark, obviously the easier it is for you to get marks, because we're not going to miss anything. So if you explain how your function works thoroughly here, then that's going to, you know, help with that process. So really, really important for assessments and also in the real world to document your functions when you write them.
So the first exercise I had was this debugging one, and the main reason I included this question is because I wanted to sort of show you my debugging process to hopefully give you some hints on how you can approach debugging yourself. So there's this function here, and there's a few things that are intentionally wrong with it. We're going to go through and find those things and fix them up together. So I've written the code out already, and you can see here there's sort of already some warnings. We'll come back to what they are. Red means that there's actively an error. Orange is, there might be something wrong, but I'll still run about it. So if you don't see those squiggly lines, odds are that you've not got the setting turned on. So if you go back to the main MATLAB screen and press the little cog with preferences, head into Code Analyzer and just check that this is ticked on. If it's ticked on, you should see those squiggly lines. So yeah, just check that if you're not getting them. I'll just clear the stuff I was doing earlier. So let's start by trying to run this code and see what happens. So I've got the function and it's got the same name, which you have to have if you have a function as the start of your code. So if I now run print stars 5, which was our example, we get this invalid use of operator error, as well as a line number it's found on. So invalid use of operator should straight away get you thinking, well, there's something that I've tried to do math with that I shouldn't have. So operator is plus, minus, multiply, divide, anything that's a mathematical operation, power, all that sort of stuff. So if I go to line 5, it's actually underlined for us, but even if it wasn't, you can see that there's an operator there. We didn't actually want to multiply something though. There's no numbers either side of that. What we wanted to do was print some stars. So we're trying to print that asterisk, not multiply with that asterisk. So effectively, we've got the wrong data type. So this is a syntax error. We've tried to use an operator, which is going to cause a problem before the code even tries to run, where we should have actually used a string containing an asterisk. So syntax errors are problems with the MATLAB language. We've written something wrong. It's kind of like we've tried to write a sentence in English, but we've jumbled up all the words, or we've, completely used the wrong grammar or something like that. So same thing applies for MATLAB. If you don't sort of structure the sentences correctly, it won't know what you're talking about. So that's that red line gone, as well as there was a little red bar over here before. It's gone now too. So let's try and run it again at this point. Print stars 5. And now we get this error, undefined functional variable number of stars on line 3. So that's just saying you've used something that you haven't actually previously defined. So maybe you've defined it after you've used it or something like that. In this case, we've actually just typed the name wrong. So here we've used number of stars. Up here we've used number of stars. And if we had hovered over that warning, we actually would have gotten that hint. It says input argument number of stars might be unused because we've never actually referred to it after that. So this is a bit of a tricky one. It sort of seems like it might be a syntax error, but it's actually a type of runtime error. So runtime errors are where the language is correct, but you try to do something that doesn't make sense, that MATLAB doesn't understand after it starts running. So one example is that it starts to loop through an array. You've got 5 elements in the array and it's looping through, except you've got it to try and check element 6, which doesn't exist. So it runs the first 5 times and then it gets to 6, but there is no 6th element, and at that point it throws an error. So MATLAB didn't know that it was wrong until it hit that point and couldn't find the value. Same thing's happening here. If we actually had code above the for loop here, it would run. And it wouldn't throw the error until it got to here. So it doesn't realize that there's a problem until it tries to get this value and goes, hang on, that value doesn't exist. So to fix that one up, we just need to name them the same thing, and you can see this has gone green now, no warnings found, so that's nice. So at this point, let's print it again. Print stars 5. And no red text, no loud dings, so that's a good sign overall. However, we're still not getting the expected output. In our expected output, we were printing 1 star, 2 stars, 3, 4, and 5 for the input of 5. Here we're printing 2, 3, 4, 5, 6, so we've always got 1 too many stars. So there's a few ways you could kind of try to work this out. One way that can be pretty helpful is to set a couple of breakpoints. So let's set a breakpoint. Let's set a breakpoint here and run the code. So let's run print stars 5. So it's going to run here. So it's gone through the for loop, through this for loop, and it's printed the first star. We can also see that at this point, I is equal to 1 and j is equal to 1. Then we can take another step and we can see it goes to the next line. And when we step again, it actually prints that star in that new line. So if we then step again, it goes back up to the for loop, it sets I to 2, j is equal to 1, and then it prints the star, and then it jumps back up to j is equal to 2, prints a star, then it leaves the for loop and prints a star in a new line. So even though I was equal to 2, and j went from 1 to 2, because we've got this extra star after the loop, that's what's causing the extra star. And we can kind of keep going and confirm that. So here we can see now I has been set to 3 in the workspace. So then j is equal to 1 at first, and then it's equal to 2, and then it's equal to 3, and it prints a star for each of those down in our command window here, and then it leaves the for loop, prints the 4th star when it should have only printed 3, and then it goes back up to the next value of I, which is 4. So then j is going to go 1, 2, 3, 4, print those 4 stars, and then it's going to print that extra star because of that next line. Then I goes to 5, j goes 1, 2, 3, 4, 5 in the workspace over here. You can see it changing, and then it prints that 6th star. So the problem is happening here. We've got 1 too many stars here, and if we get rid of that, quit our debugging, and then run the code again. Let's try that again. Print stars 5. So we actually get the whole thing working now, sorry. So you have to take the breakpoint off again when you're done with it. So we can see that that's actually matching the expected output. So that's how you can use the debugger to find logic errors. It's a really handy tool. Something I do as well is I'll print messages. So if I'm not really sure where the error is occurring, I might print some messages saying, I got to this point, I got to this point, or something like that. Print values to see if they're as expected. So you can use the actual debugger, or you can use kind of a more ad hoc approach and print stuff as you go. So that's sort of the debugging process. So we had our syntax error, our runtime error, and our logic error in this case of the additional star. And once we worked all of those out, we were good to go. Logic errors are by far the worst to find because instead of getting a line number, you have to step through all of the code. So it's a good idea to test as you go to try and avoid getting logic errors in the first place. So for example, if we had tested this code without this line here, we might have seen what was happening to that point, and that might have helped us to work out what to write here correctly.
And so that's it for our week 5 extra exercises. Next week, we'll be taking a look at some more advanced functions and data structure stuff as well. So feel free to work ahead if you want to get a bit more practice on functions ahead of the assignment. So I'll see you in the next video.